Hey guys, welcome back to another video. In this video, we're going to learn about different types of electrochemical cell. That is, previously we've seen, let's say metal ion half cell, and also non-metal ion half cell, that is hydrogen and hydrogen ion half cell. So we've seen a couple of different half cells, right? Now in this video, we are going to learn in details what the three main types of electrochemical cells are and how we draw those cells. So the main purpose of this video is to understand that how you're supposed to draw the cells in your paper, right? So drawing the cells is a question that is going to be there quite often in most papers. So you need to be careful about all the details that you mention in your labeling and in your drawing, right? So there are three main types of electrochemical cell. Three main types of half cells, right? So one is going to be metal ion half cell. That is, if you've seen the previous videos, we talked about the magnesium and magnesium ion half cell. So the electrode is made up of magnesium. The solution has a concentration of Mg2+. So metal ion half cell. The other is metal ion half cell. So you can have a solution that the electrode doesn't need to be of iron. The electrode will actually be of platinum, which is neutral, Pt. And the solution will actually have the two metal ions. So let's say Fe2+ and Fe3+. The two ions will be inside the solution, making it a metal ion half cell. The other last type is going to be non-metal ion half cell. That is, let's say in the previous videos, when you saw the hydrogen coming in through the funnelish thing, and you have your solution of H+, and this is your platinum, right? Pt. And this is your platinum wire. So H2 gets in through this space, H2. And the H+ concentration is 1 mole per dm cube. So this is your non-metal, and this is your non-metal ion. That makes your non-metal ion half cell. So three main types of half cell, and you can connect these to make other different types of electrochemical cell. Okay, so let's start off with the first type, which is metal ion half cell. You've probably seen this already, but let's understand it again. So you have in this half cell magnesium ions. Remember, always write the electrode reactions in terms of reduction. So Mg2+ gaining 2 electrons, turning into magnesium, right? Okay, so this is what you're going to focus on, this half cell, and this is your entire electrochemical cell. I've drawn it by connecting it with a hydrogen ion half cell. So in this we have the platinum wire, H+ concentration 1 mole per dm cube, and you have your H2. I'm not going to get into which one is going to get reduced and oxidized. For that, you can watch the previous videos. But in general, in short, this is 0 volts, and this is a very negative electrode potential. Since more negative, it is going to lose the electrodes. Hence, it's going to be oxidized. Therefore, current will flow from this direction to this. So this is your real current flow direction, right? Okay, so showing this is also important, your current direction, and often they'll also mention if you need to show the current direction, real current or conventional current. The conventional current in this case is going to be in this direction, I, right? And they also ask you to denote which electrode is positively charged and which one is negatively charged. In this case, it has a more negative electrode potential, which is why it is going to be to negative terminal, and this is going to be a positive terminal. Okay, so fair enough. Now let's focus on our metal and metal ion half cell. You will have your this is your platinum wire that is connected to your voltmeter, and this electrode will be made out of magnesium metal, and your solution will have 1 mole per dm cube concentration of magnesium ions, right? And you can have that by having a solution of magnesium sulfate, so such that you will add 1 mole per dm cube concentration of magnesium sulfate. Since the ratio of both are 1:1, you will also get 1 mole per dm cube of magnesium ions. Similarly, you do the same over here. Over it, I've added an example when it's not going to be 1 mole per dm cube. So yes, your concentration of H plus is going to be 1 mole per dm cube. But since you're adding H2SO4 into the solution to get 1 mole per dm cube of H plus, the concentration of H2SO4 is actually supposed to be 0.5 mole per dm cube. So let's say they just gave you H2SO4 and they kept this place blank for you to write what the concentration of H2SO4 is going to be. You won't write 1 mole per dm cube, you're supposed to write 0.5, because for each mole of H2SO4 you get 2 mole of H plus, which is why 0.5 mole will give you 1 mole of H plus. Therefore, we get 0.5 mole per dm cube of H2SO4, not 1 mole per dm cube. Okay. So I believe you're clear on this part. That is what's going on in the magnesium ion half cell, right? Fair enough. Now, I'll talk about the important question, that is, why do you have solvage? Previously, I answered shortly. That is, I mentioned that the solvage is there to make sure if the concentration of ions in either place decreases or changes, the ions from the solvage will replace that ion concentration. But there is actually a bigger reason, that is to keep the charge on either beakers or either solutions the same, such that if the magnesium ions over here, let's say, since it is losing electrons, right, this part of the solution, this half cell, will eventually get more positively charged, right? Now, to make sure that doesn't happen, so your anion from the solvage is going to get to this solution and make sure your charge over here, positive charge over here, does not build up. So to make sure the charge stays constant, the solvage is there to replace the ion concentration, or otherwise, to say it differently, to make sure your charge remains the same, right? To make sure your charge remains the same. So there is also another reason you have a solvage, that is, it completes the circuit. I didn't mention this, sorry. So actually what happens is, if I draw the circuit, so this is your circuit without the solvage. Now, if you have the solvage, you can complete this circuit and you have the complete circuit. So electrons flow from here to here to here to here, right? So you have a complete circuit. So that is why you need the solvage. Okay, so that is one. So if I talk about the charge distribution point, so specifically for the magnesium solution, notice, since it is going to lose the electrons, since it has a more negative electrode potential, the electrons are going to travel from here to the hydrogen half cell, and eventually there are going to be more magnesium ions in the solution, which is going to increase the positive charge in the beaker. Oppositely, in your hydrogen ion half cell, you're going to have a lot of the H plus ions gaining the electrons and turning into hydrogen gas and being released as H2. Okay, so the concentration of H plus is going to decrease in this solution. So less positive. So what's going to happen then is, since the positive charge in this beaker is decreasing, the cation from the salt bridge, let's say your salt bridge is made up of potassium nitrate, right? So your cation over here is potassium ion. So the potassium ion is going to go to the solution and replace the concentration of H plus. So that is what I'm actually meant by replacing concentration of the ions, right? So in this case, since the concentration of H plus is going to be replaced, your positive charge relatively is going to stay quite the same, right? So H plus gains electron, positive charge decreases as a result. It becomes more negatively, it becomes relatively more negative. So to make sure that doesn't happen, the cations, that is from the salt bridge, be it potassium, or if you have sodium nitrate, in that case it's going to be sodium ions, it's going to go to the hydrogen half cell and it's going to replace the concentration of H plus. So as a result, at the end of the day, your charge remains the same in either of the half cell. Okay. So your nitrate ion, that is your anion, is going to go to the Mg magnesium half cell, because over here notice you had a greater concentration of positive charge. So to make sure the charge decreases, the positive charge decreases, nitrate, the negatively charged ion, is going to go into this beaker, right, to decrease the positive charge, right? So at the end of the day, you're left with two solutions which constantly have relatively the same charge, and that is helpful to maintain the standard condition of the of the entire process of reduction and oxidation. Remember, in case of the voltage, the standard potential, your standard is going to evaporate away if these factors are not kept in check. That is pressure, that is charge, that is temperature. So these few things, they need to be constant, such that the voltage between the two half cells are going to remain the same, right? So fair enough. These are the few things for metal and metal ion half cell. I mean, these are the salt bridge part is also the same for other electrochemical cells. That is metal ion and metal ion half cell. So this is your second type of half cell. So in this case, notice one thing. This part of the electrochemical cell, this entire half cell is made up of two metal ions, right? So in this case, your electrode is actually going to be made up of platinum, right? Because you don't have a solid metal in this case to make the electrode. You have two metal ions in the solution. So in this case, our metal ions are going to be Fe2 plus and Fe3 plus, two in different oxidation states. And I've connected this half cell to a metal and metal ion half cell, like the previous example. So in this case, what's going to happen is your solution, make sure your solution has 1 mole per dm cube of Fe2 plus and 1 mole per dm cube of Fe3 plus. And your electrode is going to be made up of platinum. This is going to be your voltmeter. And yeah, so if let's say they've given you FeCl3 and they ask you to fill in the blanks for what the concentration is going to be, it's going to be 1 mole per dm cube, since the ratio, since 1 mole of FeCl3 also gives 1 mole of Fe3 plus. Okay. So in case of Fe2 iron sulfate, in case of iron sulfate, notice 1 mole of Fe2 plus, 1 mole of iron sulfate is going to give you 2 moles of Fe2 plus. Therefore, you don't need 1 mole per dm cube of iron sulfate. You actually need 0.5 mole per dm cube of iron sulfate. Okay. Now, in this case, to find out the electrochemical cell potential, what are we going to do? We are going to write both the electrode reaction. That is, in case of iron, what is happening? In case of magnesium, what is happening? So in case of magnesium, write it down. Mg2 plus 2 electrons turning into magnesium. The electrode potential is given to be minus 2.38. Fair enough. Now, in case of iron, you're going to write the reduction process. Again, reduction process, remember. So you're going to write Fe3 plus electron turning into Fe2 plus, right? That is going to be 0.77 volts. Now compare which one is more negative, Mg. So it's going to release electrons, right? It's going to be the oxidation part. There's going to be reduction. So now you know what is happening. Fair enough. Now in this case, your electrode potential is going to be this is your reduction, this is your oxidation. Which one is getting reduced? This one. So positive 0.77 minus 2.38. So at the end of the day, you get a very high potential difference. So this is actually a very high potential difference between two half cells. So it is going to be 3.15 volts. Now, one thing I'll mention over here is your molar ratio or your moles of the equation. That is, once you balance it out, notice Mg is actually going to release 2 electrons, right? Mg is going to release 2 electrons and iron is going to gain 1 electron to turn into Fe2 plus. So Fe3 plus actually has to gain only 1 electron to turn into Fe2 plus, right? However, to balance everything out, you're going to multiply the entire thing with 2 such that there is a transfer of 2 electrons because it's releasing 2 electrons. So to balance it, multiply with 2. However, this is not going to affect your E cell value. So never, I have made this mistake, so saying from experience, never use the molar ratio when calculating your E cell value. Your E cell value is going to stay the same irrespective of what the molar ratio or what the moles of your ions are. That is not going to affect your E cell value. The only thing that can affect is concentration. So as long as your concentration stays the same, your moles does not matter, right? So whatever the molar ratio is over here, notice 1 mole of Mg reacts with 2 moles of Fe3 plus. That is not going to matter. This molar ratio does not matter. So your E cell value is going to be irrespective of your moles of your ions, right? Great. So your E cell value is going to be 3.15 volts. Now, notice one thing, that in case of the both irons, that is iron, Fe2 plus and Fe3 plus, both has a concentration of 1 mole per dm cube. Now, over here, if you change the concentration, that is change from 1 mole per dm cube to any other value, that would have affected the equilibrium. That would have affected your electrode potential value, because the concentration of oxidized species, that is Fe3 plus, and the concentration of reduced species, that is Fe2 plus, would change, right? So that would result in a different electrode potential value, and I'm going to talk about that as well. There's a formula to find out what happens when there are changes in ion concentration, how it's going to affect your electrode potential value. Electrode potential value. And as a result, it will also affect your E cell value. So yeah, you have to keep both the ion concentration the same, that is 1 mole per dm cube. Now the last one is the non-metal and non-metal ion half cell. You mostly see it with respect to the hydrogen ion and hydrogen gas. So in this case, what you're going to have is a platinum wire connected to a platinum surface, right? That acts as the place where hydrogen ions get to gain the electrons. It's a place where the reactions are going to take place, surface area, right? So you're going to put in the hydrogen gas, right? At a pressure of 1 atmospheric pressure, temperature of 298 Kelvin, and the concentration of H plus is going to be 1 mole per dm cube, right? So this is going to be your hydrogen and hydrogen ion half cell, that is non-metal and non-metal ion half cell. Yeah, so I've written over here, your moles or amount of substance does not change the electrode potential since your electrode potential is volt, meaning work done per unit charge. What I basically meant over here is, if you remember your voltage formula, work done per unit charge. So it does not matter if you change the moles or amount of your ions, the charge traveling per unit time or the work done per unit charge, that is not going to change. The same amount of work is going to be done per unit of charge. Now this can only vary if you change the concentration, because it is going to affect the electrode potential of each of the half cell. So if only in that case will you see a change in your cell potential. Therefore, changing your moles or amount of moles is not going to do anything to your cell value, right? Fair enough. That is it for this video, and see you in the next one.